Welcome, Trent.
So,
Hi.
hey, okay.
Sorry about my flash. Do you mind if I sit in?
Oh, yeah, sure.
I just do it.
Oh, yeah.
Thank you.
We do it too much.
Your stuff.
Yeah, it didn't go too much.
Oh.
Not like everybody had like thousands.
Oh, well, I mean, you can't rely on the stock market.
No, talk about the one I got from SpaceX.
Oh, I see. I see.
Yeah.
I see.
Because everybody was talking about it last week.
Oh, I see. I see. I see. Yeah, that was,
It only gave me like 120.
I see. Big.
It's split up 3 times, but not enough to retire.
Unfortunate.
Yep.
Elon got really rich, though.
Yeah, he sure did.
Not that he did really need this, but
It's on me. We're talking about how AI is keeping them up in that. How we're just moving too fast with it and stuff like that. They're still going at it. And like,
no. I got the beat issues with it. All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? On this sprint of fluid mechanics, and so we're at it for another day today. Okay, so first thing today, there was a little bit that I wanted to finish up from the lecture from last Thursday. So last Thursday we went all through potential flow, but we stopped right before I think one of the more interesting things, and so I was thinking about skipping it, but I think it's one of those things that's especially if you're into sports, I think is one thing that you kind of see in a lot of sports, which is cool. So we'll finish that up maybe just in the first 10, 15 minutes. And then we'll move on to the next topic for today, which is called dimensional analysis. So dimensional analysis is kind of an odd duck kind of topic to have in fluid mechanics. I think there's always discussions among the fluids faculty to whether to cut this topic because technically speaking, it doesn't have anything to do with fluids. It's really just about experimental design. It's just that people always link it together with fluids, and of course it has applications in fluids. But this topic is kind of more for a lab class, but just so that you get the full experience, and then just to have a break a little bit from fluid mechanics, we'll be talking about dimensional analysis today. Okay. All right. So some announcements, and so remember, midterm 2 is this Thursday, so that's in 2 days. Thursday, June 18th. So please make sure you guys are here in class. Just like the first midterm, there are no options to take the midterm over on Zoom. So you need to be here in person. And just like the first exam, you are able to bring your writing utensil. Please bring a calculator and also one sheet of notes. So one 8.5 by 11 sheet, both sides you can write or type. Okay. Also remember that I've posted a study guide for midterm 2 online as well. And so if you check the daily page for today, week 4, part 1, you should see there's a document at the bottom for the midterm study guide. Also this afternoon, I posted the solutions for homework 3. Okay. So in terms of content, remember, midterm 2 is just going to cover control volume analysis. So that's just homework 3. So I know homework 3 was very, very long. There were a lot of problems on it, but that's basically all the problems that you need to study for the midterms. Okay. Other announcements, I did post homework 4 as well. Question from the chat: how many questions will the exam be? It'll be the same number of questions as exam 1. So there'll be 4 short answer questions and then 3 problem solving questions. Except this time, the 3 problem solving questions will all be control volume type problems. Okay. Homework 4 was posted today, or it was posted yesterday, I believe. And so, that's covering basically everything we're covering after midterm 2. So it starts with potential flow. It's going to continue with dimensional analysis. And then the topic for the next 2 days is going to be pipe flow, which I would consider to be the last, I would say, main topic that we need to cover in this class. And so homework 4, I would say not as long as homework 3, but it is lengthy as well. And so this week's going to be quite busy, I think, for everyone. So I think up until Thursday, everyone, I think, will be busy preparing for the midterm. And then right after you finish the midterm, you have homework 4 to work on. 4 is due this Sunday. Okay. And then just so that you guys are aware, I do plan on finishing up high flow this week. Next week's going to be a little bit of an awkward week because we do have the final, and I don't want to cover anything too heavy before the final exam. And so next Wednesday, I am planning to reserve half the lecture for just a review for the final. And then everything else we cover next week, we won't do too much with the problems, but I do want to cover some additional conceptual information, especially with regards to some external flow stuff. So like lift and drag, I definitely want to cover, because those are important concepts for you guys to learn this concept. Okay. So this will be kind of the last week we do kind of more intensive type problems. And then next week will be kind of more conceptual stuff and review for the final, and then the final exam as well. Okay. And just to be kind of fully transparent too, so final exam will be next Thursday in class. So that's just a week after midterm 2. That's just kind of unfortunate with the timing with the summer class, with the summer course. You'll have the entire class session to do it, so the full 3 hours. I'm going to write the exam as if it were a 2-hour exam, because that's how much time you would have for the final during a regular semester. So I'm not going to make the exam longer. It's still going to be a 2-hour exam. Just I'll give you the full 3 hours to do the exam. Okay. And then for the final exam, you can have 2 cheat sheets, so 2 8.5 by 11. Okay. So if you want to reserve your cheat sheet for midterm 2, then you can do that. But just know that there's going to be other topics that will be covered in the final exam. All right. So a lot of announcements today. Are there any questions I can answer about anything? Okay. All right, so let's go ahead and pick up where we left off last Thursday. Okay. So the last thing I wanted to cover last Thursday was kind of a question from the chat. I said 2 cheat sheets. Yes. So for the final exam will be 2 cheat sheets. Midterm 2 will just be 1 cheat sheet. Yeah. Let me write that down. Yeah, so midterm 2, 1 cheat sheet, final exam next Thursday, 2 cheat sheets. Yeah. Okay, so last thing we covered last week was this idea of combining different potential flow solutions, right? So the whole idea with potential flow is that we want to come up with a method or develop a method to solve for velocity field distributions. Okay. In other words, we want to find out different ways that velocity can vary in space. And so the general kind of workflow for this is to take the stream functions of your basic flows. And remember, we went over 4 of them. And so, just to remind you, we have uniform flow. We have the source/sink. We have 3, which is a vortex or ideal vortex. 4, we have the dub. Okay. All right, so for each of those basic potential flows, they all have their corresponding psi or stream function. Okay. Right. Remember, the stream function is a scalar function. You can obtain the velocities by taking derivatives of the stream function. But what's significant about the stream functions is that if you want to make complex flow, all you have to do is just add the stream functions of different basic potential flows together. So for example, the one example that we kind of spent a lot of time on last Thursday was the half body. The half body being a combination of the uniform flow and a source. Okay. So you add those two, you get flow over this kind of almost kind of like an oval or elliptical shaped shape, or the half body. Okay. And where we ended was flow over a cylinder. Right. So basically, by combining a uniform flow and a doublet, right? So we took the stream functions for those 2 types of flows and added them together to get a single stream function. Okay. What we obtained was a flow field that looked like the following. We had a cylindrical cylinder, right? And we had flow that was going around it just like that. Okay. So potential flow is really fascinating, and honestly, there's a lot more that we can do with it, because you can create these very complex, so oftentimes very aesthetically pleasing type flows. Of course, aesthetics are kind of opinion. I think they're nice. My wife may not think so. And you can actually do a lot of analysis for this. Okay, because typically what you do after you generate your stream function, you typically want to do 2 things, right? So you want to obtain the velocity field. Right? And the way that we obtain the velocity field is by taking derivatives of the stream function. Right, so you have your combined psi that you obtain by adding the basic potential flows together. You can take derivatives in order to obtain the velocity fields, right? So we did that, quite a few times last Thursday. And then from the velocity field, the next thing that you're typically interested in is the pressure field, right? Because every flow field has both a velocity and pressure field. Okay, and the way that we obtain that The way that we obtained the pressure field was that we took our velocity field from the previous step, and then we plugged that into Bernoulli. Okay. Because all of the velocity fields that are flow fields that we obtain from potential flow, they satisfy the conditions for Bernoulli. So they're steady state, they're incompressible, they're inviscid, so we're not considering viscosity, and we can follow a streamline very, very easily. Okay. Okay, so that's kind of the whole process, and so I know we kind of talked about a lot of stuff last Thursday, but this is kind of the workflow and kind of the main, I would say, takeaways from last Thursday. Okay, so ultimately, the goal with potential flow is to obtain these multivariable functions that represent the velocity field and pressure field, and this is how you would do that. Okay, now the last topic that we went over before we left was this flow over a cylinder, right? So we had this, water or air that's going over the cylinder, and we found a very curious result. Right? We found, by following this exact same process, and so, we took the stream functions for the uniform flow and the doublet, we added them together, we took derivatives, we found the velocity field, and then from that velocity field, we plugged into Bernoulli, okay? We obtained the following, I would say, expression for the pressure, okay? So the pressure field, as a function of theta, is equal to the following: P naught plus 1/2 rho u squared 1 minus 4 sine squared of theta. Okay. Where theta there is the polar coordinate, okay, and so that's kind of the rotation from the positive x-axis. Okay. Okay. So why is this curious, right? And so if you actually plot this out as a function of theta, right? Okay, so we basically plug in all values of theta, and so if you're expressing this in radians, you can plug in, you can express this or plot this from minus 180 degrees to 180 degrees, or I said radians, but I gave you degrees. In radians, it'd be minus pi over 2 to pi over 2. Okay, and what you would obtain is something that's perfectly symmetrical. Right, where this part of the graph here, this would be the front end of the cylinder, and this would be the back end. Basically, we would, if you get far enough away from the cylinder, you have the same pressure on the front and back. It's just the pressure just kind of dips, as you kind of go around the cylinder, but the pressure distribution is uniform. Okay. Okay. So another way to say this, right? And so, just keeping in mind that the flow is progressing this way, right? Right, so flow hits the front of the cylinder from the left and then goes around the cylinder and then goes out the back. Okay. All right, so another way for us to say this is that by the time we reach the back end of the cylinder, the pressure has fully recovered, right? So the pressure kind of fully recovers to its front end value. So we basically have the same pressure on the front and back. Now, the reason that's strange is that, remember, pressure is nothing more than just a force, right? It's essentially the force that the fluid exerts onto any solid surface that's on it, okay? If we have the same pressure on the front and back end of the cylinder, right, that means that there's no net force being applied on this cylinder in the flow direction. So I think kind of the last image that I left you guys with last Thursday, to kind of give you an analogy here, right? This means that, if you were to stand in a flow field, right? So a cylinder is, a human body is roughly cylindrical shape. And so if you were to stand up straight and stand, in the presence of, let's say a raging river, right? According to this theory here, you would not experience any force in that flow direction, right? Another way to say that is that you would not experience any drag force at all, right? And that's simply not true, right? So if you step outside and there's Santa Ana winds blowing you at 60 miles an hour, you expect to be moved along with the wind. You're not expected to be just Jesus and the flow is just going around, right? So this right here, this result is known as D'Alembert's paradox. It's not really a paradox. We understand why this is why the theory predicts this. But I think for a long time, as the field of fluid mechanics was developing, this was a very curious result that scientists really struggled to explain. Okay, so the reason that the theory doesn't predict any drag force is because, remember, potential flow ignores viscosity, ignores friction. Okay, and so what happens when you add friction to the flow? It causes the boundary layer, causes the flow to actually separate from the body and create a wake region. Okay, and so in reality, your pressure distribution is something like this, where it still comes in high, but then as you get to the back end of the cylinder, right, the pressure never fully recovers, right? And so this red curve is what happens when you have viscosity. Okay. It kind of flatlines at some value just because that's where the formation of the wake is. Okay. Now, if you look at this plot, you have a net pressure, you have a high pressure on the front, and on the back end, you have a lower pressure, right? And so because you have a difference in pressure, high pressure here, and low pressure here, right? There's going to be a net force that goes in this direction. Okay. Which is what you expect, right? And so if you're standing in the presence of the flow, you expect to be kind of swept away with the flow. There should be a net force that pulls you along with the flow, or I guess it should say pushes you. Okay. And so that's kind of the explanation. Okay. Okay. So I know I mentioned that. I know we talked about this last Thursday, but I did want to go over it again because this is kind of an important point. And we'll revisit this next week when we talk formally about lift and drag. And so are there any questions on this? Okay. All right. So the last effect that I wanted to talk about has to do with spin. Okay. Now let's take our flow under a cylinder and let's add another potential flow to it, right? And we can do that easily. And so if we just take our stream functions for flow over cylinder and let's add an ideal vortex to that flow. Okay. All right, so now we're going to get a new stream function where our stream function is the combination of the stream function for the cylinder, right? So which is what we went over last time, plus the stream function for the vortex. Okay. Right, which we went over last time as well. Okay. Remember, when you have these stream functions, you can create any combination just by simply adding them together. Okay. And we can go through the exact same exercise, which I'm not going to just because of time, where we can take this and take derivatives. Okay. You can take derivatives to obtain the velocity field. And then once you obtain the velocity field, you can then plug into Bernoulli's to obtain pressure. Okay. So I'm not going to go through the whole mathematics just because I do want to get to dimensional analysis today. We do have to finish that just so we can do pipe flow tomorrow. But let me just kind of explain to you just qualitatively what. Okay. So by adding a vortex to the flow, we're adding this kind of circular motion. Okay. So once again, let's draw our cylinder. Okay. The nice thing about adding a vortex is that it doesn't necessarily change the shape of our cylinder because our vortex is spinning with the cylinder. Okay. Okay, so just like before, we have flow going over the top and bottom, right? But this time we're adding some spin to this as well, right? Right, and so just for the sake of argument here, let's assume that our spin is going counterclockwise. Okay, so we're going, around just like that. All right. Now, this spin here is going to affect the flow that's going all around the cylinder here, okay? Because what's interesting about this spin is that, if you look at kind of the Cartesian directions of the spin, right? On top, right? On top of the cylinder, we have our spin that's going to the left, right? And on the bottom, our spin is going to the right? Just because that's how spin works. Okay? And when you combine that with the uniform flow, remember, part of flow over a cylinder is that we have this uniform flow that's kind of passing over the top. Okay. And the uniform flow is going from left to right. All right, and so what tends to happen there is that for the top of the cylinder, where our spin is going to the left, that's going to slow down the flow on the top. Okay. Because if we have spin that's going to the left, that's going to oppose the uniform flow, so they kind of effectively almost cancel out. Whereas on the bottom of the cylinder, our flow is going to speed up, right? Because the spin of the cylinder is adding additively to the uniform flow. Okay. Okay. And so that's going to affect the streamlines. Right. So I'm just going to try to draw just kind of very quickly here. So the streamlines are going to come in. You have this kind of bow-shaped thing that kind of forms here. Whereas on the bottom, we have flow that's coming around just like that. Okay. So that's the velocity field, right? So we kind of break this symmetry that we had before. Whereas, before, our flow field on the top of the cylinder, bottom of the cylinder essentially looked the same. But now we have, slow flow on top, high flow on the bottom. Okay. Now what is this going to do? So we've also kind of mentioned this a little bit before when we talked about control volumes, right? And when we talked about, when we talked about Bernoulli, right? Generally, when you have higher flow or higher velocities tend to decrease the pressure. And the opposite is true when you have flow that's slowing down, right? So when you have flow slowing down, that's going to increase the pressure. Okay. Okay. And so the net effect of this, at least on the pressure, is that you're going to have high pressure on the top and low pressure on the bottom. Okay. All right. And hopefully you can kind of see where this is going, right? So if you compare this to, this kind of discussion that we had here about pressure recovery, whenever you have a difference in pressure on different sides of a solid object, right, that's going to lead to a net force, right? Now, when you have viscosity, that's what introduces the drag force. that force is in the same direction as the flow, right? Which makes intuitive sense. What's interesting about this spin is that, there's a net force that's going to be added here, right? And we can kind of draw that in. Right? And so we have a net force that goes downwards on this cylinder here. Okay. Now, what's interesting here is that this net force is not in the direction of flow, right? Because the uniform flow is going left to right, but this net force is actually going perpendicular to that flow direction. Okay. And all we had to do that was to add spin. Okay. So if you're a fan of baseball or just pitching in general, right, you'll know that a pitcher can, a big part of baseball is making the ball when you throw the ball, do have some interesting movements to fool the batter, right? And so one way that pitchers can do this is by inducing spin. Okay. So there's a type of pitch that a pitcher can do. Well, it's one of many pitches that they can do called a curveball, but I think curveball is just the easiest to kind of demonstrate this with. Where if you look at the grip, or you look at the way a pitcher throws a curveball, he intentionally kind of flicks his wrist to kind of induce this spin. And by inducing the spin, right, it causes the ball to either rise or fall, right, mostly fall, in kind of an interesting way to kind of fool that. Okay. And so this is kind of the origins of that, or how that actually works. By introducing the spin, you literally change the fluid dynamics or of the airflow around the ball, which causes this net force to cause the ball to rise or sink as you want. Okay, so this effect right here, right? This effect is known as the Magnus effect. It's one of the really kind of interesting things about fluid mechanics because it's an effect. Once you talk about it, it hopefully it makes sense. By the way I describe this, but if you're not aware of this, if you're not aware of the fluid mechanics, it looks like magic, right? You throw a ball, you add spin on it, and suddenly the ball just kind of falls off the tape, and so which is kind of a really cool thing. Okay. Okay, so I wanted to make sure I mentioned that, I know it took a bit longer than I thought, but this is kind of one of those really cool things about fluid mechanics that I think you can kind of it's kind of a party, I call it a night party trick. Something that you can explain at a party and not look weird about making differential equations and things like that. This is something cool that you can spot. All right, any questions on Magnus effect or anything about potential flow before we move on to dimensional analysis? Okay. All right, so let's go ahead and move on to the next topic. Okay, so the next topic is dimensional analysis. Okay. Now, like I mentioned at the beginning of class today, dimensional analysis is kind of an odd duck topic to have in fluid mechanics. In some ways, it's kind of nice because we've been going 3 full weeks of just really intense fluids, and so this is kind of a little bit of a break from that. But at the same time, it's not explicitly a fluid mechanics topic. I would say it's kind of more of a general topic. Okay. So the whole idea with dimensional analysis is that it's meant to help with experimental design. Because no matter which field of engineering that you go into, whether you end up doing fluid mechanics as a career or that being a big part of your work, or if you go into solid mechanics or anything else, experiments are always going to have a place in engineering work, right? And I use the term experiments here a little bit broadly, a little bit loosely, and so when I say experiments, it doesn't necessarily have to happen in a lab or anything like that. Experiments can be anything where you test in reality and you basically observe the results. Okay. So that could be anywhere from a very carefully regulated, carefully set up, experimental setup that you would find in a lab, or it could just be, things that you observe in practice as well. Okay. Because you can do all the modeling in the world, you can solve all the equations in the world, do all the simulations, but they're kind of meaningless in a way because we don't live in the virtual world, we live in reality, right? And as well tested and as kind of reliable as the equations that we go over in this class, things like the Navier-Stokes equations, things like control volumes, right? You have to still go out and test it, right? Because there are always going to be, no matter how much you think you understand a physical system, there's always going to be factors, there's always going to be things that you may not account for in your analysis that you can only account for if you do the measurements and you set up the experiments, okay? And I say that as someone who does, for myself, I don't do any experimental work at all. So all my own research, all the work I've done is purely computational. And so I'm the biggest cheerleader for computational work there is out there. But even I know that, there's no value in computational work without the experiments to back it up. So experiments will always have a place, right? And don't let anyone tell you otherwise. So there's no better computer out there than Mother Nature, right? The problem is experiments are very expensive and very resource intensive to actually run. Okay. All right, which may not, when I think when you're coming from an academic setting or a class setting, you may not really fully appreciate what that means because you guys have taken lab courses, you guys have taken your physics labs, your chemistry labs, those experiments are not expensive, right? I had one lab, and for some reason this one always stands out to me, even though it was the most boring lab ever. I had a lab when I was in undergrad where we literally just measured gravity. We took marbles, we dropped it. We timed how long it took the marbles to drop, and we used that to estimate gravity. And we did that literally 300 times to account for, uncertainty. And, lo and behold, yes, gravity is 9.8. We didn't have to drop the marble 300 times. But in reality, expensive are very expensive and resource intensive. Right? So to give you an example, right? Let's say you work for Boeing, and let's say that Boeing has come up with a new airfoil design. Right, so this airfoil is meant to be put on the next, line of commercial aircraft, right? We've done the simulations, we've done the CFD, we've done all of the analysis out there, right? So this airfoil design should provide a boost in performance compared to the old one. But the last step is just to actually test it to see if that's actually going to work. Okay. Now to do an experiment to actually test this airfoil design in practice, and just kind of thinking of this naively. Right? If you want to test this on a real airplane, you have to build an entire airplane in order to test it. Okay. And even if you extract out, maybe some of the extraneous features, right? So, for a test airplane, there's no passengers that have to go inside. And so you don't have to put seats, you don't have to put, entertainment systems on the inside. It's still a huge piece of engineering, right? Not only do you have to build a whole airplane, you also have to build a chamber or have a way to test it. Right, and the type of building or the type of a facility that can be used to test this is something called a wind tunnel. right? So if you're not familiar, a wind tunnel is essentially a building that is designed to, for you to kind of place objects into the wind tunnel and you literally just blow wind at it at a certain velocity that you can control and you can kind of observe the results. Okay. There are wind tunnels that do exist. They are a thing. But as you can imagine, they are, very expensive to operate. Even tiny ones are not that easy to do. And so already, and these are just kind of the first two things that come to mind, right? Sounds like a very expensive, very time-intensive endeavor that's going to involve a lot of staff and a lot of, resources from the company to actually do. Okay. Now, if the airfoil works great, right? And so, let's say you build all these tests and the airfoil works out great, that's great, right? And then you can go on and move on to production from there. But what if it doesn't do what it's supposed to, right? So what if you kind of do all these things and you build all these facilities and test subjects and test products, and the airfoil does not perform the way it's supposed to, right? Then you kind of wasted all these resources and you have to go back and redesign, okay? Which, as you can imagine, is not a great conversation to have. So the whole idea of dimensional analysis is to think, maybe there's a better way to do this. Maybe there's a better way that we can design our experiments so that we don't have to go through this entire process of building all these huge structures and all these huge kind of facilities and use all these resources and still get data that's useful to us.
Like you're saying, I always thought that too, but SpaceX just uses money like crazy, just rebuilds it.
Well, SpaceX is different. They have a $2.5 trillion market cap. But most companies can't operate like that.
Okay, that rocket blew up, let's just use this.
Yeah. Most companies aren't willing to do that.
I was able to order parts, it's just like, or tools, it's just unlimited. That was crazy.
That sounds fun, but yeah, I'd like to live in that environment one day. But yeah, most of the times it's not like. Okay, all right. So that's kind of the whole idea of this subject here. And so all the examples that we're going to go over has to do with fluid mechanics, just because this is a fluids class. But this process and these concepts and these ideas you can apply to any subject within science and engineering as well. In fact, it is applied to different subjects in science and engineering. It's like I said at the beginning. For some reason, they put the burden on the fluid mechanics class to teach this, which is fine. It is cool. It is really interesting. But fluids is not exactly we don't have a ton of space in a semester of fluids to fit something like this in. But it is useful to learn. It is really cool to do. It does kind of give you a break from kind of the intense fluids that includes. Okay. Any questions on this so far? Okay. All right. So let's go ahead and move on. So the main kind of the main concept that we're going to go over is this idea called the Buckingham pie theorem. That's kind of the whole idea, the whole concept that kind of drives this entire concept. Okay. Okay. So let's set the stage a little bit. So usually, when you are running experiments, you are, trying to find something or get some data, there's usually one variable that you're interested in. At least one variable. Okay. Right. So there's some variable, some parameter. And so just to kind of bring us back to the airfoil, right? Maybe you're interested in the total amount of lift force that airfoil can generate when it's exposed to flow. Okay, so that's one of the main things that an airfoil has to do. It has to be able to generate lift. Okay. Okay. And so the whole idea with running an experiment is that, this variable or this parameter that you're interested in, it's going to depend on other variables within your system. Okay. So things like the flow speed, things like the geometry of the airfoil, things like the viscosity, things like the density of the air, right? So all of these are going to affect, say your lift force. Okay. And by running the experiment, right, what we're hoping to glean or what we're hoping to find out is basically this relationship, right? So how does our variable of interest depend on the variables of our system? Right? Does the lift go up when we increase the airspeed? Does the lift go down when we increase the thickness of the airfoil? Right? So these are kind of the questions that we want to answer. Okay. And so, this is kind of the mindset that you have to have when you're designing experiments. You have to think about, what are the properties, what are the variables that I'm interested in finding out, and what are the properties of the system that are going to affect the values of these interest properties. Okay. So as another example, okay, this one's going to be a little bit simpler than the airfoil, and we're going to basically carry this same example kind of throughout most of the lecture today. Let's do something simple. Let's say that we're interested in the pressure drop across a section of pipe. Okay. All right, so if you think back to our control volume analysis, right, think back to when we have conservation of energy, right? When flow goes from one point to another, assuming the velocity is the same, right, we can have a difference in pressure from one point to another because of things like viscous losses, okay? Okay, so to kind of visualize it, although, for this, it doesn't matter too much, but let's say we have, this is a kind of a split view of a cross section of the pipe, okay? Flow is going here from left to right. And then to drive the flow, we need a difference in pressure. Okay, so P1 is going to be bigger than P2, right? So as flow goes through this pipe, pressure is going to drop. Well, another. Okay. This is also to give you a preview of kind of what we're going to talk about tomorrow with pipe flow, right? So pipe systems, pipe flow is also a very important part of fluid mechanics, right? So knowing the pressure drop in a pipe system is a very important parameter in designing these types of systems. Okay, so in other words, if we define delta P as P1 minus P2, okay? Let's say that we want to run an experiment to measure what this delta P or this pressure drop is going to be. Okay. And so by running the experiment, we're going to basically think about what are some other variables in this system or this situation that's going to affect the value of the pressure drop. Okay. So in other words, we're going to think of other variables in the system that are going to change the result of our experiment. Okay. Okay. So I'm just going to give these. I'm just going to give these variables to you, but this is something Let's say that you are going to be applying this kind of theory out in the wild. These are other variables that you have to think of yourself, but for now, I'll give them to you. Okay. Okay. So one thing that's going to affect the pressure drop is the pipe diameter. Okay. So we'll call that D. Next would be the density of the fluid, right? So that's going to affect the pressure drop as well, whether you're pushing water or you're pushing air. Okay. Next is the fluid viscosity, right? So that's going to affect the pressure drop as well. Right, and also the velocity as well, right? So if you have a faster flow, slower flow, that's going to affect the pressure drop as well. Okay. Okay. All right, so we have basically one dependent variable, which is our pressure drop, and four independent variables: diameter, density, viscosity, velocity. Right. All right, so the way we can kind of express this kind of concisely is we can say that pressure drop, delta P, is equal to a function of all of our parameters here. So D, rho, mu, and V. Okay, so you'll see this notation yeah, a lot today. Maybe you've seen this in the previous class, but when you see this generic F, right? So this generic F basically just means that this is going to be a function of. Right, so pressure drop delta P is a function of the diameter, the density, the viscosity, and the velocity. Okay. We don't know what that function looks like. In fact, that's what we're trying to determine in our experiment. But we know that it's going to depend on those quantities there. Okay. So we have a fairly simple situation, right? So pressure drop in a pipe is something that's measured a lot and something that you should that's going to be computed no matter what. Okay. But even for this very simple situation, we have four independent variables. Right? And we want to find out how the pressure drop changes, according to each of those variables. Okay. Now, kind of the naive way to do this is to kind of, I would say kind of brute force it and to do kind of four individual sets of tests. Okay. Where each of the sets of tests, we're going to change each of the independent variables separately, right? So let's say we're checking for the diameter. And so, maybe we run 5 separate trials or 5 separate experiments with ever increasing diameter, right? We start with a small pipe, we start with a slightly smaller pipe, a medium pipe, a large pipe, and a very large pipe. Okay. And then, maybe we do the same for velocity, right? So we start with a, slow flow, slightly slower flow, medium flow, high flow, very high flow. Okay. Right, so that's kind of the brute force way to do it. And so, you just kind of do it's called a parameter sweep. Okay, so you just kind of sweep through each of the parameters individually, you vary each one, and you kind of see how that affects it. Okay. All right, but this is very inefficient, right? And so even for 4 variables, right? So let's say that you conduct 5 tests per variable, which also is not a lot, right? So if you conduct 5 tests per variable, 4 variables, you're looking at 20 tests overall. Okay. But that also doesn't account for the fact that maybe 2 of the variables kind of have a complex interaction. So maybe if you increase the diameter and velocity together, that's going to have a different effect on the pressure drop. Okay. So this whole idea of doing independent tests is very inefficient, and basically no one does this in reality. So you never want to run an experiment unless you only have one independent variable. You never want to run an experiment where you test each individual each variable independently, just because you're not going to get results in a timely manner. Okay. Okay, that's something you might tell an intern to do just to waste their time, but that's not the way that kind of real work is done. Okay. A better way is that, instead of testing each parameter or each variable individually, maybe you can test a combination of them and you kind of test the combination kind of a smart way. All right. So in other words, what if we kind of combine our variables in such a way where we say that, maybe instead of testing, D, rho, nu, and V to get, individually, what if we test this product, right? So what if we test the product rho times times the velocity times the diameter divided by the viscosity? Right. So we can see what I've done here is that I've combined our four variables here. Okay. Right. And so instead of testing each one individually, we have just one quantity here. Okay. And this one quantity is significant because if you look at this and if you check the dimensions for every single one of these variables and you multiply them together, you'll see that this entire expression here is dimensionless. Right, so density is mass divided by length cubed. Velocity is length over time. Diameter is length. Viscosity is I always forget viscosity, but it's the combination of those, right? And so if you do this whole thing, you get something that's dimensionless. In fact, this combination is a very famous dimensionless variable in fluid mechanics called the Reynolds number, which we'll talk later. Okay. Now, if you test this dimensionless variable, and then you take your pressure drop and you also make it dimensionless, where we're taking the exact same variables that we use, right? So you can see here, we took the pressure drop, we multiplied it by the diameter, we divide by the density times the velocity squared, right? So that's also going to make it dimensionless, okay? Right, we have this new function phi, right? So this phi here this means function of. Right, so by doing a little bit of legwork at the beginning and making these dimensionless groups, we've simplified our experiment significantly, right? And so instead of testing, four independent variables kind of separately, we don't know how they're going to interact, right? Instead, now we have just one variable that we can test, which is just the dimensionless Reynolds number. Which is a lot easier to do. And in fact, you can set this experiment up a little bit easier as well. Okay. Because if you think about it, right, so things like the diameter, things like the flow speed, that's fairly easy to vary, right? To test the diameter, you just get different tubes. But how are you going to test the density, right? And so you can't exactly vary the density in a fluid very easily. You have to get a whole different fluid. But a different fluid will also have different viscosity as well. And so, it starts to get a bit complicated. And so, if you do it instead according to this dimensionless variable, it becomes a lot easier to actually design and run your experiment. Okay. Now, of course, the question is, how do we determine this? Okay, so how do we obtain this dimensionless variable? Okay. Right. It wasn't just magic, right? So that's essentially what we're going to learn today. So this uses a method called the method of repeated variables. And that's going to constitute kind of the main, I would say, kind of main exercises that we're going to do in this class. Okay, so a lot of dimensional analysis is kind of is kind of just more conceptual stuff. But there are some problems that we can do. But you'll see these problems are kind of fun, especially compared to the problems that we have been doing, which have been more, I would say, more complicated. Okay. Okay. All right. Any questions on this so far? Okay. All right. So let's jump into the method of repeated variables. And along the way, we'll talk about the Buckingham pi theorem in terms of what that states. Because I know this entire section is driven by Buckingham pi, but we haven't actually stated what the Buckingham pi theorem actually is. But I think that'll make more sense once we start to go through the method. Okay. All right, and so this method here is basically a method for us to, first of all, derive dimensionless groups for any type of experimental setup that we're interested in. Okay. So just like the couple examples that we've talked about so far, the airflow example, the pressure drop in a pipe example, right? If you follow the method of repeated variables, then you're able to obtain these dimensionless groups. Okay. All right, and so the nice thing about this method here is that it is a very, I would say, systematic approach, right? And so there's not really any tricks or any kind of curveballs that can be thrown your way throughout the set. It's very systematic, and so you just kind of have to follow the steps. Okay. Okay, step one. All right, step one is, I would say, probably the most difficult step, although it's not something that you're going to be doing in this class because I will give these to you typically. But if you were to apply this same theory out in reality, this is something that you have to do, right? So step one is to list all the relevant variables for your experiment. Okay. And your variables kind of fall into different categories. Okay. All right. So the first category, the first variable that you typically will think of when you're running an experiment is you have to think of your dependent variables first. And we talked about dependent variables as the variable that you're looking to obtain from your experiment. Okay, so that would be your pressure drop in your pipe. What the lift force on the airflow. Okay, so those of course are going to be relevant, and that's one that you have to kind of keep track of. Okay, sometimes you may have more than one. Right? So sometimes you may want to obtain multiple variables or answer multiple questions from an experiment. So just make sure you list all of them. Okay. Okay, so the next question you have to ask is, after you have your dependent variables, right, using your understanding of fluid mechanics or whatever domain that you are kind of running your experiment for, and so you have to think about, what are the other variables in my system that will affect the value of our dependent variable? So some things might be obvious, right? So there'll be some variables that obviously will affect it. Okay. But there might be some that you may not know as well. Okay. And this is where things get a little bit challenging because I think sometimes people include variables that may not have an effect on their variable of interest, or they may not consider other variables or other factors that may affect it. And but you want to make sure you include that in your analysis. Okay. Okay, so I do have some tips on this. Okay, because this is, like I said, this is the only part of the whole process that's not systematic, right? So you have to use your own intuition to a degree. Okay. So first thing I would say is think about the governing equations for your phenomenon that you're trying to test. Right. So the governing equations are always a great place to start because what is in your governing equations? A bunch of variables, right? So if a variable shows up in the governing equation for your phenomenon, that's usually a good idea that you should include that in your dimensional analysis. Okay. Right. So if a variable shows up, so let's say that you're looking at a situation that is governed by the Bernoulli equation, right? So everything that's in the Bernoulli equation, you should include in your dimensional analysis, right? So things like the pressure, things like the density, low velocity, gravity may affect it, but we're on Earth, so gravity doesn't necessarily change. But maybe the height does as well. Okay. Okay, so that's the first thing to check, right? So think of the governing equations and think of what variables show up there. You should at least include everything in the governing equation. Okay. Okay, besides that, you can think of other factors of your system or other factors of your experiment that may affect your results. Okay, and then so the next three tips here are kind of categories of different variables that you can consider. Okay. So the first aspect I think is just the most obvious to think about is just the geometry of your system. Okay, things like the lengths, things like the areas, diameters, radii, things like that. Okay. Sometimes you may have a complex geometry, so there may be multiple geometric dimensions, right? Maybe diameters in different aspects. Maybe you have a nozzle, you have an inlet diameter and outlet diameter. Okay, so that's always a good place to look. That geometry will almost always affect your results. Okay? Next category of things, which, again, we're using fluids here just because this is a fluids class, but you can generalize this to solid mechanics as well. So you can think of material properties, okay? But properties that are unique to fluids would things like be like density, viscosity, velocity, right? If you haven't included them already in step one, this would be the place to include it as well. So I'd say for almost every fluid phenomenon, density, viscosity, velocity, they're going to affect your results. Okay. You may have already picked them up from step one, but it would be good just to think about it again. Okay. All right, and the fourth category would be things like any kind of external effects or external forcing that are affecting your results. Okay, so think of things like from our from our control volume analysis, things like shaft work, right? So if you're analyzing a pump, you're analyzing a turbine, and so the amount of power that gets extracted or the amount of power that you're inputting, that's going to affect your results, and so that's one thing that you want to include, right? Any kind of let's say you're looking at momentum, right? Any kind of external forces that's being applied on the fluid, that's going to affect the results as well. Okay. Okay, so like I said, step one here is the most difficult, just because it does rely a lot on intuition, and I would say the first few times you do this for an experiment, you're probably going to get the list wrong, or you may get it right, right? So part of running an experiment is determining what are the variables that affect our results. And so you consider something that maybe other people may not consider, but it may affect your results, and so you may want to include. Okay. Any questions on this so far? Okay, good. All right. One other thing that you have to think of when you're doing step one here, you're listing all the variables, is you have to make sure that all of the variables that you select are independent. And what independence means is that you should not be able to obtain, you should not be able to kind of form a very simple combination of any variables in your system that are somewhat obvious. Okay. Okay. All right. So I think this point here is a little bit easier to illustrate with an example rather than kind of explaining. Okay. So for example. So let's say you're doing step one for a given system. So let's say you're doing it for pipe flow, right? The radius of the pipe and the diameter of the pipe are not independent variables. Because radius and diameter are related by a simple equation, right? So 2 times the radius is equal to the diameter. And so when you're doing your method of repeated variables, you don't need to include both the radius and the diameter because one implies the other. So you only have to include one of these. Right, so that one's pretty obvious, right? So radius and diameter are essentially the same thing. You can't change one without changing the other in the same. Right? Another one that may not be obvious, maybe diameter and cross-sectional area, right? So cross-sectional area as well would not be independent if you already have diameter in your system, okay, or in your analysis, because diameter affects your cross-sectional area. Okay? Okay. So for our pipe flow example, so for the pressure drop on our pipe, we have 5 variables in total. Right? And so essentially by the time we started that example, I've essentially already done step one for you, right? So I've already identified these 5 variables, right? So let's take those 5 variables and let's just label them in terms of what types of variables they are, and then we'll go to a breakout. Okay, so first one is our pressure drop. delta P. Right, so pressure drop, since this is what we're interested in finding in our experiment, this would be our dependent variable. Okay. Right, so our pressure drop is going to depend on the other variables. All right, next we have the diameter. So that is the geometric quantity that we've chosen. Okay. Right, so I would classify the diameter as part of the geometry of the system. Okay. Next, we have the fluid density, rho, and so I would characterize that as a fluid property. Okay, next we have the viscosity, mu, and so I would also characterize this as a fluid property. Okay. And the last variable that we've determined that's going to affect our pressure drop is the fluid velocity, v. Again, I would characterize this as a fluid. Okay. So in this example, we don't have really any external effects. There's no external force that's affecting the pressure drop in a pipe. If there were factors that did that, then we can include it here as well. Okay. Okay. So this would be kind of an example in terms of thinking about the variables in your system and how they affect your dependent variable. Okay. It's always a good exercise, even for systems or even for situations where it's fairly obvious what your variables are going to be. It's still good. It's still a good exercise to kind of list them out. Try to think of any other factors that may influence your results and label all your variables just so that you kind of know moving forward. Okay. These labels are not going to affect, how we determine our dimensionless groups. They're just kind of good. It's just a good exercise to kind of do just to kind of build your intuition in these types of problems. Okay. All right. Any questions on that? Okay. All right. So let's take a break. Let's come back at 4:25. And so we will continue on with the method of repeated variables. From All right, it's 4:25. Let's get back to it. Okay, so just to kind of remind you where we left off, so we are going through the method of repeated variables. We just went through step one. It's interesting. We're going to spend the longest talking about step one, but step one is the one you're never going to do in this class, because I'm going to do step one for you. So step one is just choosing the variables, right? But there is a lot of intuition, a lot of kind of reasoning that goes through step one. It's just that in this class in particular, you're just not going to do it. But when you're using this method later, step one is probably going to be the most important. Okay. Okay, so now after you have your list of variable signs sorted out, now we can actually kind of begin our method. So step two Once you have your list of variables and, like we have here for a pressure drop, these are our 5 variables. Step 2 is to express the dimensions, the raw dimensions of each of your variables. Okay. So think back, to the very early stages of this summer session, which time-wise is not that long. It was just 3 weeks ago. But in terms of content, it was ages ago, just because we were going so fast, right? So by raw dimensions, I mean not its units, right? So not its SI units, although you can do that as well. But after you convert to the SI units, convert it to its dimensions. Okay, dimensions being either its mass, length, time dimensions or force length times. You can do either one. Okay. So I would say more common is to do mass length time. Mass is a bit more fundamental than force, but some cases you can do force length time as well. Okay, so the important thing is just pick one and then kind of stick with it. Okay. Okay. For instance, so let's go through our 5 variables here and let's list out their dimensions. Okay. Okay. So let's look at pressure drop first. Okay. Okay. So pressure drop is going to have dimensions of pressure. Right? So a difference in pressure is still a pressure, right? And so we're going to have the same dimensions there. Right? And so a pressure, you can refer to the table, that we kind of talked about kind of early on in this class, which list all the dimensions. Or you can just reason it out. I think that's usually the faster way. So pressure we know is a force divided by an area, right? Where a force, if we want to express this in mass, length, time units, a force is a mass multiplied by an acceleration, because F is equal to ma. Okay. Right, so we have a mass multiplied by an acceleration, which is length over time squared. And an area has dimensions of length squared. Okay. And so if we kind of work this through, we can see that the dimensions of pressure we can use these square brackets to indicate dimensions. And so the dimensions for pressure is mass divided by length times time squared. Okay. And that is in the MLT dimension system. Okay. All right. So the next variable that we have here is the diameter. Diameter is very simple. A diameter is just a length. Right, so not much to do there, so that's pretty nice. Next, we have the density. Density, remember, is a mass per volume, and so volume has dimensions length cubed, and so this is going to be m divided by L cubed. Okay, next we have the viscosity. And so viscosity is a little bit of a strange one, but viscosity, remember, has dimensions of pressure times length. And so we have pressure up there. So pressure is, pressure times time. Remember the units for dynamic viscosity is Pascal seconds, right? And so the dimensions for viscosity is mass divided by length times time. And then we have the dimensions of velocity. So velocity, the units for velocity is meters per second. And so the dimensions are length over time. Okay. All right, so step 2 of the process, once you have your variables, is just to list out the dimensions. Okay, and so remember, you can look this up in a table. Sometimes that may be useful for some strange variables like maybe pressure or viscosity, but otherwise, these are very straightforward. All right, step 3. So step 3 is where our Buckingham pi theorem actually comes into play. Okay. So step 3 is to use the Buckingham pi theorem. And what the Buckingham pi theorem is going to get you is it's going to tell you how many dimensionless groups should we obtain from this collection of variables. So for this list of 5 variables here, right, pressure drop, diameter, density, viscosity, and velocity, right, we're going to essentially what we're going to do is we're going to combine these together in order to form these dimensionless groups, okay? But we have to determine how many dimensionless groups are we even going to have, right? And that's where Buckingham pi theorem comes into play, okay? So Buckingham pi theorem, it sounds fancy just because it sounds like Buckingham Palace in the UK, but it's actually very simple. Although deriving this theorem was not simple. Okay, basically the number of variables or number of dimensionless groups equals a very simple difference. Okay, so it's going to be K minus R. That's it. But of course the question is, what is K? What is R? Okay, so K is very simple. K is just the total number of variables that you're considering. Right? And so for our example here, we have 5 variables, or our K is going to equal 5. Okay. Meanwhile, R here is the number of unique dimensions that are represented by your variables. Okay. Now, what does that mean, right? So the number of unique dimensions. We only have 3 unique dimensions, right? So if we're using our MLT or FLT system, you can only have 3, right? So the maximum number for R here is 3. And in fact, most of the time for any system of practical complexity, right? So anything that's not just super simple, right? R is going to be 3, right? So the way to count R is to go back to step 2, right? Right, and so we're going to look at dimensions for all of our variables here, okay? And we're going to see if all 3 of our dimensions are represented at least once, right? So we're going to look to see if mass is present in the variables, at least once. We're going to look to see if length is present at least once, right? They don't all have to appear in the same variable, but just across all the variables in our system, are these dimensions represented? Okay. All right, so mass is very easy. In fact, actually all three show up in the pressure drop, although that's not always the case, right? So mass shows up in the pressure drop, it shows up in the density and viscosity. Okay. So mass is represented. Length, I think length is in all of them, right? So length is represented by all the variables here. And then time is represented in the pressure drop, it's represented in the viscosity as well as the velocity. So for our particular example here, and again, most of the times this is going to be the case, all three of our dimensions are represented. And so our Buckingham pi tells us that, our value here is going to be 3. Okay. And so if we do the math for our example here, we have 5 variables in total, 3 dimensions that are represented. And so the number of dimensionless groups that we're going to have is 2. Right. All right, so very simple. So Buckingham pi, it sounds fancy, sounds British because I think the guy was British who came up with this, but it's really you're just taking the difference between these two. Okay. And just to give a bit of terminology, and so I typically use the term dimensionless group just because it's a bit more descriptive in terms of what these are. But sometimes, depending on where you read them, especially if you're following along in the textbook calls these pi terms. Right. So pi term is just another name for a dimensionless group. Okay. So don't get tricked up by the name pi term. A pi term is just the same as a dimensionless group. All right. So step 3 will tell us, how many dimensionless groups are we going to find in DNA. Okay. All right. Any questions on step 3? Okay. All right. Step 4. Okay. So for step 4, right? So in order to create our dimensionless groups, right, certain variables are going to be repeated. And what that means is that certain variables are going to show up in multiple dimensionless groups, right? Or dimensionless numbers. But to keep things simple, we're going to determine, or we're going to basically preconceive or kind of set which variables are going to show up in multiple dimensionless numbers. So we're going to choose which of the variables in our experiment or in our system are going to have to repeat. And so they're going to have to show up in multiple dimensionless groups. Okay. Now you can choose, you have a lot of freedom in step 4 here. So there's more than one way to kind of go about Buckingham pi and method of repeating variables. But there are certain combinations and there are certain, selections that are going to make things easier for you. Okay. So the criteria, so there's 3 criteria for choosing the variables that are going to be repeating. Okay. So the first criteria, hopefully fairly obvious, is that among the variables that are going to repeat, all of the basic dimensions have to be represented at least once. Okay. So mass has to be in at least one term.
length has to be in at least one term, and time has to be in at least one of the variables. Okay, you can't leave one out, otherwise you won't be able to cancel out all the dimensions. Okay. Okay, number two. Number two, so number one is a requirement, right? So you can't get away with number one. Number two is a suggestion, okay? Just to make your life easier. Try to choose the simplest variables in your system to be repeating. While you can do this with the complicated variables, it'll just make your life a lot easier to choose the simple ones. Okay. Okay. Number three, the variables that you choose must be dimensionally independent from each other. Okay. Right, so you can't pick two variables that are both a length, right? And you'll see in the next example we do after this, right? There's going to be multiple length dimensions, and so don't pick the two length dimensions just because they're both are length, and so they're not going to really help you make dimensionless groups. Okay. Okay. Number four is that whatever your dependent variable is, that one cannot be repeated. Right, so whatever your dependent variable is, whatever you're trying to find, that cannot show up more than once, right? It has to have its own unique term. Okay. Okay. Oh, number five, probably the most important one, I forgot. So the number of repeating variables is equal to R. Okay. Which means you're going to have three in most cases. Okay, because you're going to have all three dimensions represented, and so you should have three repeating variables that are going to show up more than. Okay, so those are the criteria. Okay. So again, there are multiple different ways that you can do this, but try to. So number two, I think, is the most important. So try to pick the ones that are simplest. Okay. So for our example, for our pipe flow example, let's choose the following three variables to repeat. Okay. So let's choose the diameter. So diameter is about as simple as it gets because diameter just has dimensions of length. Okay, so we have our length representative. Okay, let's also choose the velocity. So velocity also relatively simple. So velocity is just length over time, right? So we have both length and time represented. Now we need we need a representative that has mass. Okay, and the simplest term here that has mass, in my opinion, is going to be the density. Okay. So density is mass over length cubed. It's simple because it doesn't involve the time. So if you you could have chosen viscosity here. Viscosity is another fine choice, but viscosity has all three dimensions. It has both all three mass, length, and time. I find the density just a little bit simpler, just because it only has mass and length. Okay, all right. So that is step. That is step four. Okay, step four is to choose your repeating. All right. Any questions on step four here? Okay. All right. Step five. Step 5 is the part where we actually make dimensionless quantities. Okay, so step 5 is to what's called form your dimensionless groups, dimensionless numbers. All right, so the way it works is that you're going to take whichever variables are not repeating. So whichever variables that you did not choose in step 4, those are going to have their own unique dimensionless number. And you're going to multiply that by your repeating variables with an unknown coefficient. Okay. All right, so for each non-repeating variable, so we're going to make one dimensionless group based off the pressure drop and another non-dimensional group based on the viscosity. Okay, we're going to multiply that by a combination of our repeating variables, the diameter, the velocity, and the density. Okay, but the coefficients of those variables are going to be unknown, right? And in fact, we're going to solve them. All right. So to kind of illustrate this, we're going to form pi 1. Right, so pi 1 being our first dimensionless number, our first pi term, is going to be pressure drop, delta P. Okay. Your non-repeating variables are always going to have an exponent of 1, right? So don't make things complicated. Keep the exponent 1 here. Okay. So this here is our non-repeating. We're going to multiply that by our 3 repeating variables, but with unknown exponents. Okay? We're going to multiply by d raised to the a1 power times v raised to the b1 power times our density raised to the c1 power. Okay. All right, and so what we're going to do is we're going to solve for the three exponents that will make this entire combination dimensions. Okay. So how are we going to do that? So let's go back to step 2. So let's list out the dimensions. So let's represent each of these variables in terms of their dimensions. And then we're going to use that to form a linear system of equations to solve for A, B, and C. Okay. All right, so first we have the pressure drop. So the dimensions for pressure drop, remember, was mass divided by length times time squared. Okay. So that right there was the dimensions of our pressure drop. Okay. Next, we have the dimensions of diameter. And so diameter dimensions is just L. Okay. But we're raising this to the A1 power. Okay. Next, we have the dimensions of the velocity. And so velocity is length over time. That's raised to B1 power. And then finally, we have the density. And so density is mass divided by length cubed. And that's raised to the C1 power. Okay. So from here, let me write in the variables here. So this L here, that's our diameter. This length over time is our velocity. And this mass over length cubed, that is our density. Okay. Okay, so from here, we can form a system of equations in order to solve for A, B, and C in order to make this combination dimensions. Okay. Okay, so we're going to have separate equations for mass, for length, and for time. Okay. Where we're basically just going to multiply these exponents through, and then we're going to have their, that number to represent its dimensions. Okay. All right, so for instance, for the mass equation. So for mass, we have an exponent of 1 that's coming from the pressure drop. Okay. So that 1 there is coming from delta P. And then also we have a contribution from the density, which is a positive C1. Okay. Right, because for the density, our mass is in the numerator, and so we have a plus C1. Okay. And then in order for this to be dimensionless, this combination has to equal 0. Okay. And there's only one value for C1 that makes this happen. And so C1 has to equal -1. Right, so that's one of our exponents solved for right off the bat. All right, next we have length. And so length is going to be the most complicated one just because we have the most, every variable here has the length, right? Okay, so from the pressure drop, we have length that's in the denominator. And so that's going to be a -1. That -1 there being the contribution from delta P. Next, we have the contribution to length from the diameter term. So diameter is just length, right? So diameter, we are raising to the A1 power. So this is going to be a positive A1. Next, from the contribution from the velocity. So velocity also just has a length dimension in the numerator. And so this is going to be a positive B1. Okay. Right, and then finally, we have the contribution from the density. The density has a length in it, but it's in the denominator. It's also raised to a 3. Okay, and so if we combine that together with C1, I mean, granted, we already know what C1 is, but let's leave it unknown for now. This is going to be a -3 C1. Okay, because we have length cube in the denominator, so that's a -3 C1. All right, and that whole combination there has to equal 0. All right, so we know C1 already, but we don't know A1 or B1, so we cannot solve this yet. So we do have to combine that with our time term. Okay. All right, so let's do the same thing for time. So for time, we're going to look at the contribution from the pressure, right? So we have time that's in the denominator, that's raised to the second power, so that's going to be a -2. Okay. -2 contribution from the from the pressure. And then for the only other repeating variable that has time is our velocity, which again is in the denominator. It's in the denominator with an exponent of 1. So this is a -B1 here, and that has to equal 0. Okay. Okay, so now we can finally solve for this. So we can solve the last equation there. Our last equation is B1 is equal to -2. And so we plug that in here, we plug C1 in there, and what we get is A1 is equal to 0. Okay. Okay, so in this case, the diameter is actually not going to participate in the dimensionless group for the pressure. Okay. All right, and so if we recombine this, okay, All right, so our first dimensionless group here will be delta P, right? So delta P is our dependent variable. Remember, the dependent variable or your non-repeating variables do not have an exponent, okay? Next, we're going to multiply this by the diameter raised to its A1 power, and so it's going to be raised to the 0 power. Multiplied by the velocity. Velocity is going to be raised to its power, which is V1, which is -2. Okay. Finally, multiplied by the density, which is raised to its power, which is -1. Okay. So our first dimensionless group, right, keeping in mind that a negative exponent means that it's in the denominator, is, so pi1 is equal to delta P divided by rho V squared. Okay. Any questions on how we got that result there? Okay. All right. So let's do the same thing for the second pi term. So our other non-repeating variable was our viscosity. Okay. So pi2 is equal to our viscosity times diameter raised to the A2 power multiplied by velocity raised to the B2 times density, which is C2. Okay. We're going to go through the same exercise to solve for the exponents here, A2, B2, C2. Okay. Okay, so first thing, let's go ahead and replace this by their dimensions. And so the viscosity is a mass divided by length each time. Okay. Diameter is a length, okay, which we're raising to the A2 power. Velocity is a length over time, which we're raising to the B2 power. And density is a mass over length cubed raised to the C2. Okay. All right, and then we're going to do the same thing we just did. So, we're going to form our three equations for mass, length, and time. And then, use that to solve for A2, B2, C2. Okay. All right, so for mass is fairly straightforward. And so we have a, let's see, so we have a positive one that comes from the viscosity. We have a positive C2 that comes from the density. Okay. And so just like before, we have C2 is equal to -1. For length, we have a -1 plus A2 plus B2 minus 3C2 is equal to 0. Okay. Right, just like before, we can't solve for A2 or B2 here, not just yet. And so let's go ahead and bring in the time equation. Right, so for the time equation, we have a -1 contribution from the viscosity, and we have a minus B2 contribution from the velocity. Okay. So this one we can solve, and so we can solve this one to say that B2 is equal to -1. Okay. We plug in B2 in for this, C2 in for that, and we get A2 also is equal to -1. All right, and so with that, we can form our second dimensionless variable. I2 is equal to viscosity multiplied by diameter raised to the -1 power times velocity raised to the -1 power times the density raised to the -1 power. Okay, which means that all three of our repeating variables are going to be in the denominator. Okay, so this is going to be mu divided by d times v times rho. All right, and so that's it. And so that's the extent of the math that you'll have to do in dimensional analysis. So a little bit of a nice break here. So not too much, and it's all very systematic. Okay. Okay, so once we have our dimensionless groups, okay. Step 6, which I think is the most often skipped step in this process. Step 6 is just to verify that these are dimensionless. Okay. Always a good idea to check your results, and in this case, the checking results is fairly quick. Okay. And so you just have to multiply the dimensions of each component. Just make sure that they all do cancel out each other out. Okay. And then finally, step 7. Step 7 is to form your final relationship. So this part here is kind of more just window dressing more than anything, because we've kind of already done the hard work of finding the pi terms. But if you were to actually use this in an experiment, and the last example that we'll go through today does go through how to actually use this in an experiment. This is how you would actually present it. Okay. Okay, so the final relationship looks like the following. And so you're going to have, first of all, you're going to have the pi term associated with your dependent variable on one side. Okay. Right, and so in this case, it's going to be delta p divided by rho v squared. Okay. So this right here, this is our dimensionless number involving our dependent variable. Right, and so what we're going to say and the argument we're making is that our dimensionless variable involving our dependent variable is going to be a function of all of the other dimensionless variables in our system. All right, so it's going to be equal to phi of mu divided by diameter times the density times the velocity. All right, so that statement there, that not really an equation, but this kind of relationship that you can express mathematically, this is kind of what we're aiming for. Okay, because now what we can do, now that we've identified the non-dimensional numbers, we can use this to design our experiment. Okay. All right, any questions on this before we do a couple more examples? Okay. All right, so let's do, so that example, that was kind of a very drawn out example. So, we kind of drew that out over the course of an hour. So let's go through the same process again with another example, but this time we'll go a bit faster so you can kind of see kind of the whole process kind of go through very quickly. Okay. All right, so for this example, we're going to look at a fairly kind of realistic problem here. And so we're going to determine the drag force on a freeway sign. All right, so I'm sure you've all seen this, and so you're driving along the freeway, and you kind of and you have those signs that tell you that your exit is half a mile away, 2 miles away, things like that. It's basically a giant rectangle, which you don't think too much of just because it's a rectangle with words on it. But when you make a structure that big, and you have to make it out of something durable, right? So just because generally speaking, you don't want those falling on people. You don't want to go there and service them very often either. And so usually you're going to make this out of something durable, like a heavy metal, something like that. Okay. But by being so big, it's also going to catch a lot of wind as well, right? Because you have cars that are driving past it constantly. Oftentimes these freeways are kind of elevated off of the regular traffic, and so you have atmospheric winds coming at it as well. Okay. All right. So if you have a freeway sign, we're going to estimate it as just a giant rectangle here. And we're going to look at a situation where we have a very strong wind, a very strong gust that's going to be impinging right onto the surface of the onto the rectangle. Okay, so we're going to have flow that's coming in. Okay. It's going to hit the rectangle here. It's going to hit our sign. Okay. Okay. And of course, it has to go around. Right, and so if you think back to our flow around a cylinder, this means that there's going to be a drag force just because a wake is going to form. Okay, so our fluid that's coming in, it has a certain velocity v, it has a certain viscosity mu, has its own density rho. Okay, right, so not all that different from our pipe flow, right? And so generally, if you're looking at fluids, these three culprits are going to be they're kind of always there, right? So velocity, viscosity, density. Okay. We also know the physical dimensions of the sign as well. So we also know the length or the width, I should say. So this is going to be the width of the sign. And we have the height as well. Okay. Okay. And just like the title of this example illustrates, we are interested in finding the drag force. Okay. Okay, so we'll call that FD. All right, and then what we've determined, just based on our knowledge of fluid mechanics, is that the drag force is going to depend on the other 5 variables that we have here. So drag force is going to be a function of velocity, viscosity, density, height, and width. Okay. So for this problem, what we aim to do, right? So based on the variables that are given to us in this problem, we want to determine a set of non-dimensional parameters or non-dimensional numbers that describe this situation. So in other words, we're going to use our method of repeating variables to determine what these non-dimensional numbers are going to be. Okay, so we're going to follow our seven-step process. Really, it's kind of just a 5-step process, in order to determine what these call. All right, any questions on just the setup for the problem? Okay. All right, so let's start our 7-step process, but in fact, step 1 is already done for us, right? Because these are the variables. Okay. So like I mentioned, I'm not going to put you guys in a position where you have to determine the variables yourself. It does take experience, it does take intuition to determine that. And I want everyone to kind of go through the same process. And so I will give you the variables, right? So step 1 will be done for you. Okay. Okay, so we're going to start our method of repeating variables from step 2. Okay. Remember, so for step two, we are going to list out the dimensions of each of our variables. Okay. All right, so we have 6 in this case, and so it's a little bit more. But 2 of them are just length, and so it's not too bad. Okay, so let's just go one by one. So first we have a force. Okay, so the dimensions for FD here, and we're going to choose to be in the MLT dimension system. Okay. Right, so if you feel more comfortable in the FOT system, that's that's fine as well. Okay, but I just prefer MLT. So for a force, the dimensions for force is mass times acceleration. So it's mass times length divided by time squared. Okay. Next, we have the dimensions of velocity. And so velocity, just like our previous example, is in length over time. Right, next we have viscosity. And so viscosity is just like before, mass divided by length times time. After the viscosity, we have density. And so density is a mass divided by volume. So that's mass divided by length cubed. Okay. And then finally, we have our 2 length dimensions. So we have the width and the height of the sign. Right. So they both have dimensions of length. Okay, so the geometric dimensions in this case are pretty straightforward. Okay, all right. So listing out the dimensions pretty nice, pretty straightforward. Step 3. Okay. So step 3, remember, this is the part where we use Buckingham pi to determine how many dimensionless groups that we're going to have. By the way, I realized today I'm kind of using the terms dimensionless group, non-dimensional number, dimensionless number. I'm kind of using them all interchangeably. They all kind of mean the same thing. And so they all just kind of refer to just a number that doesn't have dimension. So I apologize if it's been confusing, but those all kind of mean the same thing. Okay. Okay, so remember, so for Buckingham pi, we just simply take the difference of k minus r. Where k here is the number of variables that we have. Where the number of variables in this case is 6. Okay, so a little bit more than our previous one. Okay, and r here being our number of dimensions. And so once again, we have all 3 dimensions represented. So we have mass, length, and time all there. And so r is going to be 3. Okay. So the number of non-dimensional numbers, the number of dimensionless groups in this case is 6 minus 3, which is all right, pretty straightforward. Okay, so most of the time, again, you're going to have all 3 dimensions represented, especially for fluids, because for most fluid flow, you're going to have velocity, viscosity, and density, and across those, mass, length, and time are always all represented. And so most times, it's going to be number of variables minus 3. That's how many dimensionless groups that you're in. Okay. Okay, step 4. Step 4 is to choose our repeating variables. Okay, so out of our 6, remember, we're going to choose which ones are repeating. Remember the rules here. So remember, your dependent variable which in this case is the drag force, cannot be a repeating variable. That has to have its own pi term. Okay. And for the repeating variables, we want to keep it as simple as possible. Okay, so make sure you choose ones that don't have, all three dimensions in it. Okay, so our selection here is going to be very similar to our previous example. Right, so we're going to choose the width of the sign. We're going to choose the density of the fluid and the velocity. Now you could also pick the height of the sign as well instead of the width. That's fine as well, but you do have to pick one. And so I chose the width here, but there's no reason to kind of favor one over the other. Okay. So now that we've chosen our repeating variables, now we are going to form our dimensionless groups. And so this is where we're going to multiply each of the non-repeating variables by repeating variables and solve for their exponents to make them dimensions. Okay. Okay, so let's just go right down the list here. Okay, so we'll start with pi 1. So pi 1 will be the non-dimensional number associated with the drag force. Okay. So this will be drag force multiplied by the width raised to the A1 power times the density raised to the B1 power times the velocity, which is raised to the C1 power. Okay. Okay, so just like we did before, let's go ahead and replace this with the dimensions of each term here. Right, so for the drag force has dimensions of mass times the length divided by time squared. Okay. Width of the sign has dimensions of L raised to the A1. Density is a mass divided by length cubed raised to the B1. And velocity is length over time raised to the C1 L. Okay. Okay, so let's go ahead and form our three equations, right? So one for the mass, one for the length, one for the time. Okay. Okay, so this is actually going to play out very similarly. The only thing that's different is that our first term here has different dimensions. Okay, so for the mass, you have a contribution of 1 that's coming from the drag force, and then a contribution of a plus B1 coming from the density, because that density has mass in its numerator. Okay, so if 1 plus B1 is equal to 0, we can solve this straight up. So B1 is going to equal to -1. Okay. All right, for the length, you have a positive 1 plus A1 that's coming from the width. You have a -3B1 coming from the density, plus C1 coming from the velocity. Okay. So just like our previous example, length is probably your most common dimension. So that's usually going to be in all three of your repeating variables. There's usually no way around that. Length is just very common. Okay, so we can't solve this straight up, right? So we can plug in for B1, but we don't have enough equations to solve for A1 and C1. And so we do need the time equation here. Okay, so the time equation, we have a -2 that is coming from the drag force, and then we have a minus C1 coming from the velocity is equal to 0. Okay. And so we get C1. C1 in this case is equal to -2. Okay. Okay. All right, so now that we know C1, we can plug it into our length equation as well as B1. Okay. As we plug all that in, we get 1 plus A1 minus a -3 from the B term and then a -2 from the C1, we get a 2 plus A1. That means A1 must equal to -2. Okay. Okay. So that means our first pi term is going to be drag force. Okay. All of our pi terms here are in the denominator, and so this is going to be drag force divided by the width squared, multiplied by the density, multiplied by the velocity squared. All right, any questions on how we got that pi term there? Okay. All right, so that's the first pi term. Okay, that one is unique from the previous one. Okay, our second pi term. This is going to be the pi term involving the viscosity. Okay, so we have viscosity multiplied by the width raised to the A2, multiplied by the density raised to the B2, multiplied by velocity raised to the C2. Okay. Okay. So we can go through this again, but if you compare this to our pipe flow example, we did a pi term that was identical to this, right? So for our pipe flow, we also had a pi term that involved viscosity. The only difference was that instead of the width, we multiplied by diameter, but dimensionally they're the same. So width and diameter both have a length dimension. And so just in the interest of time, I'm going to go ahead and refer back to the previous example. Right, so this would just go through the exact same thing. In fact, the previous pi term that's the third time we've seen it. Okay, so hopefully you guys are getting the hang of it. Right, and so pi 2 in this case, just like before, all of our exponents here are going to be -1. Right, so we have a mu divided by the width times the density times the velocity. In fact, this combination of terms here is a very common non-dimensional number that we'll talk about just right after this as well. So it's not surprising that this makes an appearance. In fact, this non-dimensional number should make an appearance in almost any fluid mechanics phenomenon as well. Okay, good. All right, pi 3, the last non-repeating variable. So the last non-repeating variable is the height of the sun. Okay. Now, for this case right here, this is going to be very straightforward because we know height has dimensions of length, right? In fact, this is kind of a breath of fresh air because it's the first time we're making a pi term that doesn't involve all three mass, length, and time. Okay. So for a very simple case like this, you don't have to go through the entire song and dance. There's a very simple non-dimensional way to non-dimensionalize this. So this is very valid to do. So you can just say that by inspection, we can non-dimensionalize this very easily because one of our repeating variables also has dimensions of just length, which is the width of the sun. Okay. And so by inspection, pi 3, the only way we can non-dimensionalize it based on our repeating variables is we're just going to divide it by the width. And that's very valid to do, right? So you don't feel like you have to go through the whole song and dance, and non-dimensionalize these and go through the exponents when there's something kind of very simple and straightforward, just like that. Okay. Okay. All right. So any questions on those two? I know I kind of just waved my hand and kind of determined those, but that's kind of the meat and potatoes of this example here. Okay, all right, so that's step 5. So now that we have our pi terms, step 6 is to verify. Okay. Right, so always good to check your work. I mean, you don't have to write it down explicitly, but just check just to make sure, right? Because you never know when you might make a simple mistake. Okay. Right, and then finally, step 7. Step 7 is to just form the relationship. Okay. Right, so remember for the relationship, we are going to take our pi term or take our non-dimensional group that has our dependent variable, which in this case is the drag force, put that on one side of the equal sign, and all of our independent pi terms will be on the other. Okay. Okay, so our pi term associated with our dependent variable is our drag force. Okay, so we have drag force divided by the width squared times our density times the velocity squared. Okay, this is equal to, it's going to be a function of viscosity divided by the width multiplied by the density times the velocity. That's our first non-dimensional group. Or second one, excuse me, that's pi 2. And our second non-dimensional group is h over w. All right, and then right there, that is your final result. Okay, good. All right, so Buckingham pi, the method of repeated variables, it seems very tedious to do, I think, when you first see it. But I think once you kind of start to get the hang of it, and once you start to see that most fluids problems involve kind of the same variables just over and over again, it's always going to be velocity, density, viscosity, so they're always going to be there. And so, you'll start to see kind of patterns with these. So, this section here, like I mentioned, this is kind of a nice break. Kind of near the end of the session, but a break is always welcome, nonetheless. Okay. Okay, and so for the last 20 minutes of class today, just so that we're still on theme here, there is one other section I want to go over, which are common non-dimensional numbers in fluids. Okay. So in particular, you should notice that this guy kind of appears all the time, and that's not by coincidence. So, but we'll probably talk about that tomorrow. But one thing I wanted to talk about today is, how can we actually use this to design an experiment? Because that's kind of where we started our discussion today. Okay. So how can we use a result like we just went over in order to actually design our experiment? Okay. Okay. All right. So generally speaking, when you're designing an experiment for any kind of engineering application, most of the time you're going to look to try to scale your experiment. And so what that means is you're going to take your real life phenomenon that you want to find data for, and you're either going to scale it down to be something more practical, or sometimes you'll be surprised. Sometimes you'll have experiments or you'll have phenomenon for very, very small things like microfluidics. Sometimes you need to scale it up so that you can actually observe it more easily. Right? Okay. So that's how we typically make it more practical, right? So if you think back, think back to the beginning of class today, right? We talked about running an experiment on a new airfoil, right? Where, if you were to do this naively, you would build an entire airplane, you build a wind tunnel that's big enough to hold an airplane, and then you'd run wind tests on that, which is just, really, really expensive and really, really not practical, to just test one airfoil, okay? But, if you really did want to get experimental data, maybe you don't have to build a full-scale airplane. Maybe you build an airplane that's a lot smaller than that, which is, maybe something you can 3D print, something that you can much more easily do. And then instead of running it in a gigantic wind tunnel, right? Maybe you run it on a smaller wind tunnel, one that you could fit inside a room like this, which is a lot less resource intensive than you would need to do. Okay. Okay. All right. So the key to this, is that you can't just scale down willy-nilly, right? You have to scale down in an intelligent way. Okay. So when scaling an experiment, and that not only includes just the physical dimensions, but you're going to see it's also going to involve the scaling of the boundary conditions as well. So scaling of the velocities, sometimes the densities and viscosities, but most of the time you don't have to change that. Okay. What you need to make sure is that the values of the non-dimensional numbers in your theoretical kind of full-scale experiment match the values of the non-dimensional numbers in your scaled down or scaled up experiment. Okay? In other words, the non-dimensional numbers should match, okay, between the two full scale and the scaled up or scaled down. Okay. And so the idea is that if you can get those non-dimensional numbers to match, right, by altering, by tweaking not only just the size, but also other properties as well, then the results of what you obtain will be applicable to the full-scale experiment as well, in terms of the non-dimensional variables. Right, so we're going to do one more example in the last 15 minutes today to kind of walk through what that actually means. Okay. All right, so this process of taking a full-scale phenomenon and scaling it down, most of the time you're going to scale down to fit kind of an experimental apparatus or to make it more practical. This is called similitude. And it's basically it's an essential concept. If you're going to work in any kind of testing, experimentation, at the industry level, right? Sometimes companies will run full scale experiments, and so just there are practical reasons for that. Most of them are media related, just so that they can show off kind of their big kind of wind tunnels and stuff like that. But most of the time, most of the testing you're going to be running scaled down. And you're going to utilize this similitude. Okay. Okay, so let's go ahead and do an example, right? Not really a new example, but this will be kind of building off the example that we just did. Okay, so let's design an experiment where we want to measure the drag force on a freeway sign. Okay, so let me go ahead and draw our situation once again. Okay, so we have a rectangular freeway sign. Okay. We need some numbers on this now. And so let's say the width of the sign is 35 feet. The height is 20 feet. Okay. Okay, so there's actually huge. Actually, this might be a billboard. It might not be a freeway sign, now that I'm thinking about it. Okay. Okay. And so our fluid that we are going to be hitting it with is going to be air. Okay. Right, so air has its own viscosity and its own density, and what you're going to see is we're not going to modify that. That's a little bit hard to do. Okay. But we do know the velocities, okay? And so in this case, the velocities for the air that are coming in, they are going to be governed by the Santa Ana winds. Okay. And Santa Ana winds vary anywhere between 10 miles per hour to 60 miles per hour. Okay. All right, so we want to design an experiment, but let's say that we are limited. We can only build a prototype where the maximum our height could be is only 5 feet, right? Because we have to fit it into our test chamber, right? Okay. Right, so that's our limitation, right? So that's one limitation for our experiment here. Okay, so what we want to do is we want to determine the values for all the other variables such that our experiment will have similitude with the full scale phenomenon. Okay. All right, and there is a little bit of freedom here, and you're going to see that we're going to take advantage of that, right? Because the values of some variables are just not practical to vary, right? So usually those are going to be the intrinsic properties of the fluid, right? So it's usually not practical to change the density or the viscosity of the fluid, especially for air. That's actually very difficult to do. But there are ways that we can still modify things to make sure our non-dimensional parameters are still met. Okay. Okay, any questions on just the setup in terms of what we're trying to achieve here? Okay. All right. So remember, the goal in designing an experiment like this, is first of all to pay attention to our constraints, but also to make sure that all of our non-dimensional numbers have the same value. Okay. Okay. So the first variable that we're going to determine for our experiment is the value of W. Okay, because that's going to be the easiest one to do. So first, let's check for a non-dimensional number that involves H and W. right? In fact, we have one that is very simple. Okay. Right, so one of the non-dimensional numbers that we determined in the previous example, and we did this one by inspection, is h over w. Okay, so h over w has to be the same from our physical full-scale phenomenon to our experiment. Okay. So this ratio of h over w has to be preserved between the two phenomena. Okay. All right, so this one's pretty straightforward to do. So all this is basically saying is that our sign has to be in the same, the ratio of the height and the width have to be the same. Okay. So if we look at the full scale model, right? The full scale model has a height of 20 feet and a width of 35 feet. Okay. Right, so the ratio of the height over width is 20 divided by 35. That has to be the same as our experiment. So our experiment, remember, has a limitation of a total length of 5 feet, so a total height of 5 feet. But our width is unknown. Okay. All right, so this is pretty simple, so we can just solve for it, right? And so we can basically say that W is equal to 5 multiplied by 35 over 20, which if we plunge it into the calculator very quickly, this gets us a width of 8.75 feet. Okay. Pretty straightforward. So just the ratio of the height and width has to be the same. So that's in fact, I think most of the time, even without going through this entire 3-hour lecture, I think most people would be able to determine. Okay. Okay. Next, we have to determine the other parameters. And so the other parameters in our problem are the flow velocity, the density, and viscosity. Okay. Now, we have to make a decision here. So we have to make a decision. So we know that our conditions are going to be different from our experiment because our experiment is using a smaller sign. But we have to be a little bit strategic in terms of which variables that we're going to change. Okay. Now, since our working fluid here is air, right? Like I mentioned a couple minutes ago, it's very difficult, not impossible, but it's very difficult to change the density and viscosity of air and do it in a practical way because air is just all around us, and so it's very easy to just capture air around us and just pump it through a chamber. Okay, and so in this case, since we are working with air, okay, not practical. Okay. It's not practical to adjust the density or the viscosity. Okay. If we can avoid doing that, then it'll be nice. Sometimes it's unavoidable. Sometimes you have to do it, right? So like for instance, in the field that I work in, which is blood flow simulations, for people that do experiments, based on how the dimensional analysis works out for blood flow analysis, you really can't get away from the viscosity. But actually, a lot of the experiments on blood flow, they use a mixture of what's it called name is escaping, but you have to use a fluid that is more viscous than water, and it's a mess to deal with. And so, but luckily for this, we can avoid it. We can just use straight up air. Okay. Okay. But that means we do have to modify something in order to keep the other dimensional quantity consistent. Okay. So if we look at our other pi term, the one that doesn't involve the drag force, right? We have the viscosity divided by the density times the velocity times the width. Okay. Okay, so this was our other pi term. This was our other non-dimensional quantity. And so this also has to be consistent between the full-scale phenomenon and our experiment. Okay. So just like we did with the width, let's go ahead and set up an equality relationship between these two. Okay. Okay, so on the left-hand side, I'm going to call this, I'm going to give everything a subscript f. So f to be full scale. Okay. So this will be full scale. And on the right, we have the experiment. So we have mu e times rho e, mu e, w e. Okay. All right, so we've already determined, or we've already said, that it's not practical for us to adjust the density or the viscosity. And so we're going to assume that that's going to be the same in both scenarios, right? And so we're just going to cancel those out, okay? Because those are, it's not practical to change those, okay? So that means what's left is the following. And I'm just going to go ahead and invert this too, just because I know they're both in the denominator. But we have a VF, WF has to equal to VE, WE. Okay. Okay, so we actually have everything in this relationship here except for the velocity, the air velocity that we're going to use in the experiment. Okay. Because we know the width of the full scale, right? So the width of the full scale is 20 feet. Okay. Or excuse me, the width of the full scale is 35 feet. Okay. And the width in the experiment we just determined is 8.75 feet. Okay. And the velocities, we're going to actually vary the velocities from 10 miles per hour to 60 miles per hour, because that's what's modeled by the Santa Ana lines. All right, so we plug all that in, and what we get is the velocity in the experiment must be 35 divided by 8.75 times our range of 10 miles per hour to 60 miles per hour. Okay. All right, so what you can see here is that for our experiment, in order to maintain similitude, right, in order to make sure that our experiment results are consistent, we have to speed up the flow, right? So we're using a smaller sign, but with that smaller sign, we have to speed up the flow in order to make this similar, okay? And so our velocity in our experiments, okay, we do 35 divided by 8.75, that's just 4, okay? So that means our speed has to be 4 times as big for our experiment. And so the wind speed we have to be working with is we vary from 40 miles per hour up to 240 miles per hour. All right, and so if we make those two changes, and so the nice thing is that we can still use air as our working fluid, right? But we do have to speed it up in order to make sure that we're consistent. Okay. All right, any final questions on this before we wrap it up for today? Okay, all right, so when we come back tomorrow, there are a couple, just a few minor points on dimensional analysis that I want to finish up, and then we're going to start our final kind of big topic in this class, which is pipe flow. Okay. All right, so thank you guys for coming today. Hope you guys have a good rest of the evening. Make sure you guys are studying for midterm 2. If you have questions, definitely send me an email. Come to office hours. I'm always available during those times. But I hope you guys have a good rest of the evening, and I will see you all tomorrow. Yep. You are, Chris. Yep. Pastor Julio, did you have any final questions before we wrap up the call? I don't have speakers here, so you guys have to type in chat. Okay. All right. I'm gonna sign off then. If you have questions, you can guys can email me.